Good evening, everyone. I'm Anesh Ambikar, PMRF and PhD candidate from Aerospace Engineering, ISC Bengaluru. Welcome to the Week 4 interaction for the NPTEL course, Engineering Mathematics 2. The course code is NOC 23MA25. This course is offered by Professor Jitendra Kumar. In this Week 4, Professor taught us about Taylor series expansion, how to calculate, say, radius of convergence. How do we go about calculating what is residue and how do we go about calculating it? Then using Cauchy integral formula as well as yeah, along these lines. So as well as Laurent series. Yeah. So with that all in mind, we'll be beginning with this week's curated problems. Okay, the first problem asks us to calculate the value of the integral I is equal to circular integral over the curve C 3z plus 5 upon z square plus 2z with the curve C given by norm of z equal to 1. How do we do about this? I'll first draw the curve C. This is my origin O. C is a circle with a radius 1. So it will intersect the x-axis at plus minus 1 and it will intersect the y-axis at plus minus I. So here's my I, here's my minus I. And we are asked to calculate the value of I. Uh, a quick look at the denominator tells us that our numerator is 3z plus 5 and our denominator is z square plus 2z. A quick look at this denominator tells us that its factors are z into z plus 2. We'll be writing the numerator. We'll be writing this whole thing as sum of partial fractions. So the numerator 3z plus 5 must be expressed as a linear sum of factors of the denominator, which is alpha times z, is beta times z plus 2. We can see that alpha plus beta should be equal to 3 and 2 beta should be equal to 5, which gives us beta equal to 5 by 2 and alpha equal to 1 by 2. Therefore, my integral would look like integral over c 3z plus 5 upon z square by 2 is nothing but, we established that 3z plus 5 is nothing but alpha z plus beta z by 2. So we can just write it as, we can rewrite it as alpha z plus beta times z plus 2 upon z into z plus 2 whole into dz, which is nothing but circular integral alpha upon z by 2, which is half by z plus 2 dz, half by z plus 2 plus 5 by 2 upon z whole into dz. I'll just split this integral into two parts. The first being half. The first, I'll take half outside, so I essentially have 1 upon z plus 2 dz plus 5 by 2 times circular integral over the curve C 1 by z dz. So 1 upon z plus 2, right? So if we want to find the root for z plus 2, we essentially have x equal to minus 2, whereas my curve C, which is clearly outside my curve C, and therefore using Cauchy integral theorem, we essentially have half times this thing should vanish. So we essentially have this term should vanish. So we have 0 plus 5 by 2 times integral over curve C. I can rewrite this as 1 upon z minus 0 dz z equal to 0 lies inside my point, lies inside my closed curve C. Therefore, using Cauchy integral formula now, we essentially end up with, I'll just carry on this on the left hand side. So this is equal to 0 plus pi by 2 times integral 1 by z dz over the curve C, which is nothing but 2 pi I. We have already seen this in the previous class as well. So our net integral value turns out to be 5 pi I, which is option number A. With that clear, we now move to problem number 2. So problem number 2 again asks to calculate an integral, but this time for a different integrand as well as a different curve. So we are asked to draw it for z minus I equal to 2. So again it's a circle. This is y, x, and z equal to I, 2i, 3i, 0 minus I. This is how my circle would look like. Cuts y-axis at 3i and minus I. This is my origin and this is my circle with radius 2. Okay, with this being clear, we essentially now move to our function. I'll write it as 1 upon z square plus 4 whole square. If you see z square plus 4, it can be factorized as z plus 2i, z minus 2i whole square. This is nothing but 1 upon z plus 2i whole square upon z minus 2i whole square. If this is a bit unclear at the moment, we'll come to this quickly. So, so if I have to write, I have to write my integral. If I write now my integral I, it is nothing but integral over the curve C 1 over z plus 2i whole square upon z minus 2i whole square dz. You can see that z equal to z equal to, so z naught, if you take z naught equal to 2i, we can see that this essentially lies inside the curve C, and this represents the form f of z upon z minus z naught raised to n plus 1. From Cauchy integral theorem, we know that nth derivative of f of z at z naught is nothing but n factorial by 2 pi I circular integral f of z naught upon z minus z naught whole raised to n plus 1 dz. Z naught should be enclosed in curve C. In our case, f of z is nothing but 1 upon z plus 2i whole square for our case, and n plus 1 equal to 2, meaning n is 1. So if you want to calculate integral I is equal to f of z upon z minus z naught whole square dz, it is nothing but 2 pi I by 1 factorial first derivative of f of z at z naught. If we essentially take f dash of z, it is nothing but minus 2 upon z plus 2i whole square whole cube into 1. So if I take the first derivative, so at z naught, it is nothing but f dash at 2i, since z naught is 2i. So I written it. z0 is 2i for our case. So this essentially turns out to be minus 2 upon 4i whole cube, which is minus 2 by 64. I cube is minus I. So 1 by 32i, and our integral is essentially 2 pi I by 32i. This is nothing but pi by 16, which is option A. Now we move to the third problem. We are asked to calculate the radius of convergence for a power series which is given as follows. So in our power series, summation a n z raised to n is nothing but summation n factorial square upon 2n factorial into z raised to n. Therefore, my nth coefficient is nothing but n factorial square by 2n factorial. If I want to take radius of convergence, it is nothing but limit n tends to infinity 1 over an plus modulo of an plus 1 by an, which is nothing but limit n tends to infinity modulo of n factorial square upon 2n factorial into 2n plus 2 factorial upon n plus 1 factorial square, which is nothing but limit n tends to infinity. So uh, n factorial square upon n plus 1 factorial square would be nothing but 1 upon n plus 1 whole square, and 2n plus 2 factorial upon 2n plus 1 2n factorial would be 2n plus 2 into 2n plus 1. So we can cancel 2n plus 2 with 1n plus 1, and therefore we essentially have limit n tends to infinity twice of 2 minus 1 upon n plus 1, which is nothing but, as this will go to 0 as n tends to infinity, so we end up with 4. So for this particular problem, radius of convergence turns out to be 4. We now move to the fourth problem. We are asked about the Taylor series expansion of f of z. F of z equal to 1 by z, about z equal to 2. So we have f of z equal to 1 by z, f dash of z is nothing but f dash of z is minus 1 by z square. Similarly, if I take f double dash of z, it is minus 1 into minus 2, which is 2 upon z cube, and so on. My Taylor series expansion series about z equal to z naught would be, so f of z is equal to f of z naught plus z minus z naught by 1 factorial into f dash of z naught plus z minus z naught by 2 factorial into f double dash of z naught, and so on. In our case, z naught equals 2. Therefore, f of z is nothing but 1 by 2 plus z minus 2 by 1 into minus 1 by 2 square plus z minus 2 whole square by 2 factorial, which is 2, into 2 by 2 cube These two will cancel out, and we essentially have half plus z minus 2, half minus z minus 2 by 2 square plus z minus 2 square by 2 cube, and minus and so on, which if we look to the options is nothing but option A. So that clears one problem from Taylor series. Now we are asked to calculate the residues at singular points of f of z equal to z by z plus. So what we'll do is we'll first write it in terms of partial fractions. So alpha times z plus 1 plus beta times z minus 2 is nothing but z, which implies alpha plus beta to be 1 and alpha minus 2 beta to be 0, which means 3 beta is 1, which means beta is 1 by 3, alpha is 2 by 3, and therefore f of z is nothing but 1 2 by 3 upon z minus 2 plus 1 by 3 upon z plus 1. This gives us our uh, values. So if we want to use basically the residue theorem, so firstly we want to find the singular points. A quick analysis of the denominator shows that it will be singular when z equal to minus 1 or z equal to plus 2. These are two singular points. Moreover, these are all, so these are isolated singularities of order 1. Therefore, if you want to calculate the residue as suppose z tends to minus 1, it is of f of z, it will be nothing but limit z tends to minus 1, z plus 1 into f of z, which is limit z tends to minus 1, z plus 1, z upon z plus 1, z minus 2, which is minus 1 upon minus 3, which is 1 by 3. Similarly, if I want to calculate residue at z tends to 2 f of z, it is nothing but, again, first order, so we'll directly multiply it, z minus 2 into f of z, limit z tends to 2, which is limit z tends to 2, z minus 2, z on z plus 1, z minus 2, which is 2 upon 3. So our answers turn out to be 1 by 3 and 2 by 3, which is option B. Next, we want to write the Laurent series expansion of f of z equal to 1 upon z minus 2, 1 z minus 1. Again, we will use partial fraction, alpha times z minus 2 plus beta times z minus 1. This should be equal to 1, which gives us alpha plus beta is 0, and minus 2 alpha minus beta is 1, which beta is 1 and alpha is minus 1. Therefore, our f of z turns out to be minus 1 upon z minus 1 plus 1 upon z minus 2. which if we rewrite it for norm z less than 1, it's nothing but 1 by 1 minus z minus 1 upon 2 minus z. So if I expand the first thing, 1 upon 1 minus z for mod z less than 1, so 1 upon 1 minus z is 1 plus z plus z square plus z cube and so on. This is nothing but summation z raised to n from 0 to infinity. And when norm z is less than 1, again 1 upon 2 minus z is nothing but 1 by twice of 1 minus z by 2. I'll take the half outside and then expand for norm. If norm z is less than 1, norm of z by 2 will also be less than 1. So we essentially write this as summation z by 2 whole raised to n 0 to infinity. Therefore, if I combine those, if I just rewrite this, it's essentially summation from 0 to infinity 1 by 2 raised to n plus 1 z raised to n, and hence my f of z can be written as summation from n equal to 0 to infinity 1 minus 1 by 2 raised to n plus 1 whole raised whole into z raised to n, which is the first. So in this case, since norm z is less than 1, we can just write it as the way we have done it without thinking about the negative powers of z. Okay, now we are asked to find the residue for f of z equal to z cube plus z raised to 5. So we'll first see z cube plus z raised to 5, which is nothing but z cube into z square plus 1, which is z cube into z minus I z plus I. We note that we have the following isolated singularities. So it's 0 with order 3, I with order 1, and minus I with order also again 1. So if you want to find the residue of z equal to I using at z equal to I using residue theorem, it's essentially it is nothing but limit z tends to I z minus I inverse of z. So we only have it order 1, limit z tends to I z minus I f of z is nothing but 1 by z cube z plus I z minus I. Substituting we get 1 by I cube into 2i. I raised to 4 is nothing but 1. So it's essentially half, which if we look through our options is option B. Now we move to problem number 8. We are asked about f of z equal to 1 by sine z and asked whether it has simple pole or something else. We can write 1 by sine of z to be equal to 1 upon. Now we'll use the Taylor series expansion of z sine z in terms of around z equal to 0, which is z minus z cube by 3 factorial plus z raised to 5 by 5 factorial and so on. If I take the z outside, it's 1 by z, 1 minus z square by 3 factorial, z 4 by 5 factorial, so on, which is 1 by z times We can write this in as 1 minus z, so 1 plus z square by 3 factorial plus z 4 by 5 factorial minus z and so on plus some higher order terms, in the series, which is nothing but 1 by z plus z by 3 factorial plus z cube by 5 factorial plus again higher order terms. So we note that for this particular, in this Lorentz series expansion, our principal part is 1 by z, and it only has a single term. Therefore, and the singular point is z equal to 0, is a simple pole. Which means that if we multiply the whole thing with, if we multiply, if we, so it has a, we can multiply it with z to find, so z equal to 0 is a simple pole, which is given by option A. Problem number 9. We are asked to calculate the value of the integral I is equal to circular integral over the curve C z e raised to 1 by z dz. So, and the curve C is given by norm of z equal to 1, which means that our curve C is again a circle, unit circle around origin, and we essentially have f of z is equal to z times e raised to 1 by z. And we have, if you notice it, we do have a singularity, an isolated rather singularity at z equal to 0. Therefore, if I want to write the Lorentz series, so essentially, if I want to write the Lorentz series about z equal to 0, essentially f of z, z e raised to 1 by z, which is nothing but z times 1 plus 1 by z plus 1 by 2 factorial 1 by z square plus 1 by 3 factorial 1 by z cube and so on, which is nothing but z plus 1 plus 1 by 2z plus 1 by 6z square and so on. If we look at this thing, we essentially get that our residue is the coefficient of z raised to minus 1 term, or 1 upon, or the coefficient of z minus z not raised to minus 1, which in our case residue is essentially half, which is b1. And therefore, if I take the integral value over the curve C, f of z dz is nothing but, since it's an isolated singularity, it's 2 pi I into b1, which is pi I. So we have ending up with option B. Uh, Finally, we move on to the 10th problem. So for this problem, we have I sine of 1 by z dz. Uh, Again, C z equal to 1 is again a unit circle about origin, and sine of 1 by z has a singularity, or rather singular point Z equal to 0, an isolated yet essential singularity. If we take the Lorentz series about Z equal to 0, sine of 1 by Z is nothing but 1 by 3 factorial 1 by Z whole cube, or which gives us residue of Z equal to 0 of f of Z will be nothing but 1. Therefore, my integral value is 2 pi I. The residue theorem, it is summation of the residues which lie inside the unit circle. Residues of the singular point which lie inside our curve C, which is 2 pi I into it. Okay, so which is nothing but option A. So that covers the content that I had for this week. If you have any more doubts, you can either ask them or post them on the discussion forum. That's all. Thank you for your time and attention. I'll see you next week. Thank you.